lots of stuff going on here. We're definitely coming to the end of it, or at least I'm coming to the end of it because I got nothing left. I'm running out of steam. Haha, no pun intended, because I run my games on Steam. So it's what did we do in the last video? We talked about we have the address here, and we could just look at the pointer. We don't even have to double click on it or anything like that. We just go to add address manually. We type in this address that's pointing to. We get the value. We enter some input. It converts to a bit pattern, stuffs it in the address, and we're done. So what we're going to do now is we're going to double click on this. That's a lot of offsets, and indeed it is. So what are we looking at here? Well, what we're saying is essentially this is equivalent to Shadowrun.exe, which is what we were typing in the earlier videos and whatnot. So we have Python27.dll plus some insane amount of or some hex value, 2C, 2F, B8. It's convenient. In fact, it's 6 digits. Well, 6 hexadecimal digits, but what is it? I suppose it's 24 binary digits. So anyway, that points to some location in memory. What is the value of that location in memory? Well, it's or points to some memory location, and the bit pattern of that memory location is this. So we go up here to the next offset. It takes this bit pattern and it adds some hex value onto it. This essentially it's pointer arithmetic. So what it's doing, gets this, and then it takes this, and then it goes up here to another offset. Adds the hex value of 20 and more pointer arithmetic. What is pointer arithmetic? Well, essentially that's sort of how computers do offsets and whatnot behind the scene. What you can do is in low level languages you can in lower level languages you can essentially say I know what the value when you pull the memory how am I gonna say this? A pointer is a variable, and the variables have names, they have memory locations, and then they have values. The only difference, as we talked about, is that a pointer has pointers, just like regular variables, have names. They have memory locations to store their values in, and then there are values, and their values are memory locations. When you do pointer arithmetic, what you're doing is you're pulling the memory location out of the value of a pointer, and then you're adding some value to it. And then when you do that, this is essentially how you apply offsets behind the scenes, under the hood. And that's all we're going to say about that. You can jump onto Wikipedia or Google it or whatnot, and find out all sort of ridiculous details about it. But essentially, offsets are pointer arithmetic. So pulling the value out of whatever this is right here, we're getting that. We're going up here, we're adding 68 onto whatever we got out of this memory location, and we're getting this, going back up here to or not even back, but we're going up here to the next offset. We're getting this memory location, which is essentially this. It's not even essentially, but this is always going to equal what this is. So the value of the previous offset is always going to be the base address of the offset of the of the next level of indirection. As you can see, 22A5108, 22A5108. Well, what is the address for this offset? It is 22A5180. What do we got down here? We got 22A5180. So again, we're proving the point. So we get that, we're adding 68 to it, we get that, we're adding 20 to that, we're getting this, we're adding 50 to that, we're getting this, and then we're going up here and we're saying, yep, we're no longer dealing with pointers, we're dealing with an actual value, so we're going to take this, we're going to add 40 to it, and we're just going to dig out whatever value we get, and that it happens to be 22A518. And once we get the value of that location, we get 50. Because that's what we set up here, and that's what we set down here. We could change it. Well, we can't change it because Cheat Engine sort of has rules about that and whatnot. But anyway, this is essentially how you build tables. So that when you download a table with Cheat Engine, what people have done before you download that table is they have gone through this laborious process of the pointer scanner and things like that. And they have essentially populated the table with pointers of this sort of caliber, so that when you download a table and we're going to delete this one, and there are items sort of sitting down here and they have P and things like that and whatnot, you're like, how the fuck are people figuring this out? Well, now based on this video series, you double click on it, you're like, how are people figuring this out? Well, they're doing exactly, are they using the pointer scanner? It's possible they're not. They might be using the manual method. That's what we'll get into next. But basically what they're doing, they're finding pointers, they're reducing levels of indirection, and they're finding patterns of offsets relative to some module or some process in memory that allows them to predetermine where certain values will be. And that is in the most absolute abstract way. That's what we just did here. I mean, to apply this sort of process to something like Python, like, am I a programming god? No, but I'm very impressed that we're even able to figure this out, even though we got some spurious results in the last video towards the end, where I was kind of starting to question whether we had it all right or all wrong. Why did that happen? I don't know. We'll sort of start it and restart it a couple times, see if we can reintroduce that stuff. See if we can maybe narrow down why that happened. If we can't, then I'm not really going to worry about it. Maybe I'll screw around with it after. Yeah, we definitely want to keep the address list. Maybe I'll screw around with it a bit after the video. It said some low value like x equals 5. Yeah, see, I don't know. We're getting some let me think about that. X equals 5, and we're setting larger values, and it worked for larger values. Let's make this 8. So maybe that what's going on? I'm willing to bet that maybe that's what's going on. We're gonna troubleshoot this live. Fuck it, we're gonna do it live. So we're gonna do that. Come on, restart. Reattach. Yep. Alright, so what we're gonna do instead is we're gonna say x equals some large number. Let's do 6 digits. 1, 2, 3, 4, 5, 6. Yeah, see, we get it now. We get this value now. But if we close it, and then restart it and reattach it to the process. Yep. And we say x, let's try 4 digits. Is that what I want to do? What are we dealing with here? We're dealing with data types, 4 bytes. What's the next smaller? It's 1, 2, 3, 4, 5, 6. What's that value? That value is over 65,000, which is going to be the 2-byte value. Let's try that. Let's do 65,000. What is it? Is it 35? Alright, 65,535. That's the 2-byte value. That is working. Let's make that 5. Let's see what we get. If it's not immediately obvious what we're doing here, that's fine. If you really, no, if you really followed along and you got all the stuff we're talking about, then maybe this makes sense. But what we're doing is we're just troubleshooting the problem. Yep. I bet if we set this to 65,534. There's got to be there. I'm willing to bet that if so, what am I doing here? What I'm thinking in my head is that there's some relation between the memory address that we have here, or the offsets and all that we have here, relative to the size of the value that we're stuffing in to the variable in the Python interpreter. Because behind the scenes, I bet Python is saying, for example, when we do 1, 2, 3, 4, 5, 6, Python is examining that value, that bit pattern of whatever that is, and saying, how much space do I need to allocate for that bit pattern? And then it's allocating that memory, associating with this. But when we do x equals 5, it's saying, how much space do I need for 5? I need much less space than I do for 5. I need much less space for 5 than I do for 1, 2, 3, 4, 5, 6. And I bet that's why our offsets are off here. Our offsets are off. So let's see if we can prove that. We did 65,000. Let's just do 6550. Alright, that's working. Because it's still a 16-bit value. Okay, so now when I'm thinking about it in those terms, 16 bits is what it's doing. We need to reduce it by 4 bits or 8 bits. Yep. Again, it is really, really esoteric stuff. So we're gonna say x. We associated it. Yeah, we did. So what are we gonna do? We want to knock off 1 byte for Python's dynamic memory allocation. So what we want to do is 16 bits of 65,000. So we want to be well under the 1 byte or 8-bit value. So we're going to do 250 so that we're not off by 1. I'm willing to bet that when we hit enter here, this value is not going to be 250. There you go. All right. We are not absolutely insane. We have somewhat figured it out. If we set this to something above 256, it's not going to work because it's going to make the new son of a bitch. It is. All right. Well, let's say x. I don't know, 100. How about that? Nope, not going to work. 255. That's not what we want. X equals 255. Nope, not working. X equals 256. Yeah, again, there's all kinds of crazy stuff going on right now where it's allocating memory. But see if we can prove the point a little bit to prove why. Let's see if we can prove what was going wrong and the fact that I'm not absolutely crazy. We have sort of identified the problem, or at least in my head, I've identified the problem. I believe I know what it is. So what are we going to do? We're going to say x equals 255. Again, I'm starting to talk fast. We're jumping right through this. I don't want to run out of time. I'm definitely not going to make another video about what the hell was going on. So what was going on? What was going on is that we had figured out the pointer for this offset relative to a 4-byte value because we were putting in huge numbers to make the bit pattern random. And so now when we were putting in smaller values and things like that, Python was dynamically behind the scenes saying, hey, I don't need 16 or 32 bits, as the case may be, to fit the value. X equals 5, I don't need 32 bits for that. So it's allocating a smaller level of memory. So whenever it's, it wasn't a fixed location. Again, this is sort of the trouble that you're going to run into with dynamic values or dynamic languages, as the case may be, because they do all sorts of crazy dynamic memory management. But if we keep this byte, or if we keep the value of the first variable at 1 byte, it will probably show up, or it will not show up correctly over here in Cheat Engine because it's reading the wrong offset relative to the data size. And if we make it over 1 byte, it will read the correct value. So let's make sure, or let's sort of screw around with that. 255 is what, am I off by 1? I don't know, but we're going to say 255 is not going to read the correct value over here. Nope, not going to read the correct value. So we're going to go here. We're going to redo that, attach to the process. I'm almost positive right now that this is what's going on. X equals 256. Nope, not going. That's not right. So maybe there's some more subtlety going on. So we're going to reattach the process. We'll keep incrementing by 1. Oh no, we'll go with 257 because it's possible I'm off. There you go. 257, added 1. Now it's working. Make it 0. Again, the offsets relative to the data type, relative to the data size. It's probably a better way to say that. What is x? X is 0. Just to prove the point, we will go back in here. We're not even going to do that. We're going to go here. We're going to open up this. Go to YouTube. Click some videos. I don't know. We'll watch ourselves. Nope. Do we want to do that? No. We just want to chew up memory. Open some tabs. Chew some shit up. Make the memory shuffle around a little bit. Alright, we've done that. Fire this back up. What better way to allocate memory than to fire up a 230 meg game? There we go. Allocated, deallocated. Memory's definitely shuffled around right now. So reattach it. Again, this is sort of the esoteric troubleshooting that you're going to do. Are you going to do this sort of dynamic stuff, with the game? Maybe it's possible you may do some of the stuff, but what we had attempted here in the last couple of videos dealing with a Python interpreter, it's not guaranteed you're going to deal with this kind of crap because reasons we'll get into. But we do x equals 256. We get the value 415 over here, even if we change it to 0, if the thing doesn't crash or something like that, what's the value of x? Still 256. Python says, or Cheat Engine says, I'm putting values in, there's, again, 466, 68. Well, what is that about? Well, it's because we didn't use big enough, we didn't use enough bits, essentially what it is, relative to the pointer size that we were searching for. Because when we started this whole thing, we said that all pointers were 4 bytes, and again, we were like, oh, there's some discrepancy to that, yeah, but we'll never have to deal with that. We're never going to talk about it. Well, this is why we have to deal with that, and this is why we're dealing with this. So to prove the point, just double check, because again, I'm sort of burning out here. Do that. What is x? X is 256, which is what we made it last time. We will add 1, and this is going to work. There you go. 257. Why is this working? Or rewatch the video if you want to know why that's working. But this is the sort of esoteric crap that you're going to get into when you start shuffling around addresses. We have proven the point beyond any doubt. We could shut down the computer. We could save this cheat table. We could shut down the computer, restart it. This series of offsets relative to whatever Python 27.dll is, which is a dynamically loaded library, but we're not going to talk about that. Whatever, relative to whatever this address is in the absolute RAM of the computer will always give us the value of the first variable in this Python interpreter. Now, if that's what we're going to say, and we'll, if we want to expand on that or whatever more than we already have and beat this to death, then we can certainly do that in future videos.